So last class we were discussing the DC motors, right? And we finished the DC motors part. And I hope we will be able to solve all the problems in the book. Okay, so if you would have any doubt, you'll face any doubt, you can consult me. Or you can send an email to me. I will write back to you. Okay, so today we'll start a new topic, that is synchronous generator. Okay. So what is synchronous generator? It is basically a generator which produces the AC voltage, or you can say AC power also, right? Fluctuating power and fluctuating voltage. Why I am talking about fluctuating power? Is the power really fluctuating? Is the voltage is fluctuating, of course, because you have seen DC voltage is constant and the AC voltage is constant. But is the power really fluctuating? Is it? No. Power remains constant. Power also fluctuates. If we'll derive the instantaneous power from the instantaneous voltage and current equation, because you know voltage, the AC voltage we generally take V equal to Vm sin omega t and I equal to say Im sin of omega t plus theta with a phase angle theta. Then if we'll find the instantaneous power, let us say Vi, if we'll multiply these two, you will get an expression which is fluctuating, right? But in fact it will have two components. One component will be real power, other component will be reactive power. And if we'll derive, in fact you will find it, but we are not talking about those things here because it is part of the power system course. So in your power system you have studied in your No, you have not studied, right? You have studied, But he is telling is okay. So you'll study maybe next semester. Next semester you will study. Okay. In the real power component also, you will find a fluctuating component. But if we'll take the average, it is constant. So therefore we always consider the average power. Therefore the average of the real power has some value which actually we call it active. Okay. But in case of average, if we'll take the average of the reactive power, it will be zero average. So now we'll talk about both real and reactive power, okay? Because we are talking about now the AC power or AC voltage or AC current, right? So now a synchronous generator, as the name suggests here, it operates always in a synchronous state. That means the speed of the generator remains constant and that it maintains at the synchronous speed, right? And it produces the AC voltage. So this is a typical figure you can see of an also synchronous generators are known as alternators. There are varieties of names. So because they are producing the alternating voltage and current, it is known as alternators. Okay. So now you can see here, this is your main rotor part and this is your starter part, which is mentioned here, right? So the starter part, as you can see here, this is your starter part, right? So on the starter, in case of DC generator, we have seen on the starter the field is placed and on the rotor the armature is placed. So by that, what advantage we get? Because if we see the basic principle of a generator, when we put a coil inside a uniform magnetic field and we try to collect the voltage from the two terminal, it will produce an alternating current, right? Alternating voltage, in fact. But as in case of DC generator, as it is rotating, as we put the armature winding on the rotor, we put the commutator circuit or commutator segment, which in fact helps us rectifying the voltage, right? So we get a rectified output, that is DC output or DC voltage, okay? And that is how it is very essential to put the armature winding on the rotor in case of DC generator. But now the question is, why we need to put the armature winding on the starter in case of an alternator or in case of an synchronous generator? It would have been operated best if it is put on the rotor, right? Suppose in the armature the rotor is there and we can collect it through the slip rings. So 2 slip rings we can put with 2 brass contacts, we can collect the voltage, alternating voltage and current. But why it is essentially required to shift or interchange the positions of the field and the armature circuit? Why it is essentially required? Because generally the alternators are huge size. Perhaps you have not seen, only you have experience of diesel generators. Have you seen diesel generators?
Yes, sir.
Here we have diesel generators, right? But if you will go to the power plant, you will find very huge synchronous generators, very, very big size. It starts from the 500 megawatt to 1000 megawatt, very huge size, and the voltage level it produces at around 10 kV or 11 kV, the terminal voltage of the generator. So therefore, we cannot collect such high voltage at the rotor circuit, because when the rotor rotates, if we try to collect it from using the slip ring, the high voltage, it is quite difficult and it produces spark. Okay, so therefore it is very, very difficult. Okay, so therefore purposefully if we put the armature winding on the starter circuit, there is no need of any slip ring or any brass contacts to collect the voltage and current. Directly we connect the supply to the transformer, then transformer steps up the voltage and the power is being transmitted, right? So here, therefore the armature circuit is purposefully put on the starter and the field winding is put on the rotor. Now the field winding has to produce a constant magnetic field. So how we'll get that constant magnetic field? We need to excite it through DC source, right? Okay. A permanent magnet may not work in a huge generator. We cannot have a huge permanent magnet like in case of DC generators. It cannot work. So therefore we need to excite it from the external source, and it must be a DC source. But generally we have the AC source. Externally if we'll see, the generator also produces its own AC power, or else we can have AC source from others, right? So that AC source needs to be rectified before feeding it to the rotor circuit. So with the external rectifier circuit, we need to rectify it, and the DC quantity will be fed to the rotor circuit, right? So this is your, you can see here, this is your exciter system where we need to rectify and we need to feed the DC to the rotor or to the field through this brass contacts. So this is your slip ring and these are the 2 rectifier circuits. Okay, through the rectifier circuit and the brass contacts, it will feed the to the field winding which is placed on the rotor of the machine, right? So there are varieties of arrangements you will study in your power system perhaps, but now we will not discuss. So in order to make this design, this exciter for the synchronous generator, there are varieties of arrangements. There are pilot exciter we call, and sometimes it is called static exciter. There are varieties of arrangements, and sometimes it is excited through another DC generator which is placed on the same shaft, right? So, but the most recent one is, which is as per the standard of IEEE, The most recent is the static exciter. Through the static exciter, we excite the field of the generator, right? Okay. Now we can see a figure, figure of the rotor circuit with salient poles. There are two types of fields or field structure we can see generally. One is your cylindrical structure, and other one is your salient structure. Okay. Salient structure means it has saliency, and cylindrical means it is completely round shaped. Okay. So already we have seen this, how the EMF is induced in the previously also I told in case of DC generators, how EMF is being induced, and we know inside the generator, DC generator also, the AC is being produced, right, as we see here. This is your flux, this is your EMF. So can you tell me what is the angle difference or phase angle difference between the flux and the EMF? Lagging or leading? Which one is lagging?
EMF is lagging.
EMF is lagging to the flux, right? So remember this, it is useful. So now this is your flux, this is your EMF. And we are getting the EMF in this form, that is phi p sin theta d theta by dt. And when you substitute theta with omega t, omega is the electrical speed of the rotor, then we'll find phi p omega sin omega t. And of course there are variety, here it is we have 6 poles, here we have 4 poles, there is a comparison, and we found for both. So this electrical angle, already we have discussed this, p by 2 theta m, that is mechanical angle, and similarly your electrical speed will become p by 2 omega m. This is just a revision because it is required for your to know this. It is very important to study this synchronous generator. Now your frequency, of course we found this, and then omega m is 2 pi by 60 nm, already we discussed this, and f is p by 120 nm, nm is in rpm, and nm is 120 f by p, right? So now we can see here that in case of DC generator, the armature was here in the rotor and the field is on the stator. Now just we'll reverse it. We'll just say that the armature is on the stator, okay, and the field is on the rotor. So will there be any difference in EMF? In the waveform of EMF, will there be any difference? No difference, right? And we are considering here single coil or single phase system, right? Now we'll talk about 3 phase, okay? So this is a 3 phase machine, we can say. As we distributed the single phase winding around the armature, similarly we can also distribute 3 phase windings around the armature spatially 120 degree apart. That means each of the coil axis or each of the phase axis, each of the phase winding axis will be apart. Like the phase winding axis, suppose here for phase A will lie here, then for phase B it will lie here, and for phase C it will lie here. As the rotation is in this direction, therefore it is lagging. We can see the phase B is lagging to phase A and phase C is lagging to phase B. If the rotation is in this direction clockwise, then of course phi B will be here, it will be B, it will be C, right? So these 3 phase windings on the starter, they are actually distributed manner around the armature in the slots, and the axis of each of the coil for each phase, they are apart 120 degree apart from each other. Okay. Now if the rotor having poles or having the field, it will rotate inside this armature, right? Now it will produce a EMF. So how it will produce in phase A? Suppose in phase A, like we are seeing here, red one, phase A is sinusoidal will get. Then how it will produce in phase B? Of course, the EMF which will be produced in phase B will be 120 degree away or 120 degree apart from the phase A, right? So therefore we can see here the yellow one is phase B, which is plotted, and that is apart from 120 degree from phase A. Similarly for phase C, it will be 240 degree away from phase A, right? So 240 degree away from phase A, or 120 degree away or 120 degree lagging from phase B, right? Now if we'll write the equation for each phase, the induced EMF in each phase, so already we know the equation. Here we got the equation, right? Phi p omega sine omega t, let us say sine omega t. Now EB will be how much? It will be phi p omega sine omega t minus 120, right? And EC will be phi c omega or phi p, because flux per pole it is, so therefore sine omega t minus 240, or you can say it as plus 120, right? You have read already 3-phase circuit, right? In your first year BTech course. Okay. So this will be your induced EMF in each of the phase, right? So now, if we'll find the RMS value of EA, so what will be the RMS value? Can you tell me? This is for each coil. Now for NC number of coil, it will multiply NC in each of the phase voltages, right? So it will be number of coils per phase, right? So then it will be NC phi p omega by root 2. It will be the RMS value, right? Okay. And similarly, the angle will be 0 here, and EB will be NC phi p omega by root 2. Angle will be minus 120, right? And similarly, your EC will be NC phi p omega by root 2. Angle will be plus 120, right? Okay, these are the RMS values or RMS expressions for the voltages, right? EA, EB, EC, right? Now we'll see the equivalent circuit of the synchronous generator. So like we have seen the equivalent circuit of the DC generators, DC motors, right? So we'll talk about now the equivalent circuit of the synchronous generator. Now you can see here the input to the generator will be the shaft power, that is Ts omega S, right? And we are feeding another power to the field winding, that is Vf, and if the current is flowing in the winding, then the power in the field winding will be Vf If, right? Okay. Now if I find the armature equivalent circuit, then obviously we have an induced EMF, EA, right? And we have the armature resistance, because there will be certain resistance of the armature coils that will be represented by RA, and XD is the reactance of the armature circuit, and here Z is the load and VA is the voltage across the load. Okay. Already those who have performed this experiment, particularly of the synchronous generator, open circuit and short circuit test, they might be knowing this equivalent circuit, right? Okay, now considering this equivalent circuit, we'll get different phasor diagram, because phasor diagram is very prominent in analysis of AC circuits, not for the DC circuit, because already you have seen in case of transformer, phasor diagram plays very important role, right? So now because this is a AC circuit, we need to have the phasor diagram. So let us say in this circuit the load is having unity power factor. Okay. So unity power factor means your IA is in phase with VA, right? Okay. So now how can you draw the phasor diagram for this? Like you have to, I'll tell you to represent VA, EA, IA and other parameters. How I'll represent this? So for unit power factor, if I'll draw the phasor diagram, first I need to draw the reference phasor. Okay. So what is the reference phasor here? Let us say the reference phasor is your voltage which is across the load, right? What is that? It is VA. So VA is the phasor which is across the load. Now this is your VA. Now it is, because it is unity power factor, so IA will be in phase with VA, right? Okay. Now I need to put IARA. So IARA will be in the same direction as VA, right? Now I need to add JFIAXA. Okay. So which direction it will be? It will be lagging or leading? Lagging to whom? To which? To VA. That means it will be here. ऊपर lagging होगा? ऊपर तो leading हो जाएगा ना? Is it leading or lagging? वो जो सो रहा है उसको उठा दो. वो नींद आ रहा है क्या? You can go to hostel. Take rest. Watching movie in the hostel night? Which lab? Lab report. So laborious. Whole night he gave for the lab report. Yes. Sorry? You're not getting exactly what? थोड़ा silent रहो. I can actually I need to understand what is. Oh, it's an inductor, so it should lag. Therefore, we are telling. It should lead. Why it will lead? Why it will lead? It is inductive, of course. So the voltage in inductive coil should lead by 90 degree to the current, right? Yes. So it is very easy. So therefore it will lead by IAX. Okay. Now your voltage, generated voltage will be here, EA. Okay. Okay. Now if I want to draw for the lagging power factor, so for the lagging power factor, what will happen? Lagging power factor. So now for the lagging power factor, the current will lag the voltage, right? Terminal voltage. If say the terminal voltage is here, VA, current will lag, right, by some angle, right? Now in phase with the current we will have IARA. Already you have done this in transformer, right? Many times you might have done. So, and this will be your J of IAXA, right? And this will be your EA. Okay? I hope it is clear to all of you. Now for the leading power factor, we can see very clearly that EA is greater than VA for unity power factor and lagging power factor. but for leading power factor it may not be. Like let us draw it for leading power factor. VA, IA, right? Here it will be IA, RA, then it will be J of IA, XA, and here it is EA. Okay, so therefore EA is smaller, the magnitude of EA is less than the VA for the leading power factor. Therefore, it is in contrast to the DC generator. In DC generator, your EA was always greater than V, right? The voltage, terminal voltage. But here, the terminal voltage may increase, or it can become greater than the generated voltage also for the leading power factor. Okay? So now we can see the equivalent circuit considering the armature reaction. Here we will consider, already we considered armature reaction in case of DC generator also, right? So here also we are going to consider armature reaction in case of AC generator or synchronous generator. So if we will now consider the armature reaction, what impact it will have? So the armature reaction, actually what it means, armature reaction means the EMF, actually it will produce a flux which is opposing to the main field, right? So now here the armature reaction, whatever flux it will produce, we can have an equivalent EMF, and that equivalent EMF, if we can subtract from the net EMF, that will give us, that is of course vector subtraction, not magnitude subtraction. So by the vector subtraction, if you can subtract the EMF equivalent to the flux produced by the armature reaction, then we'll get the effective voltage, right? Okay. So now let us see it. So here in this diagram, what you are seeing, this is for unity power factor. Okay, because here we are seeing the terminal voltage and current are in phase, right? And IA, RA there, of course, here, and before that your flux, let us say the flux is 5P, okay, that is flux per pole is 5P. Now your induced EMF in the generator will lag 5P by 90 degree, right? Okay, it will lag by 90 degree. Now your phi AR, so phi AR is the flux due to armature reaction. Due to armature reaction, in short I can write AR, okay, armature reaction. So now what should be the direction of phi AR? Because it is because of the armature current, so therefore it must be in phase with armature current, right? So therefore we can see here phi AR is plotted here in phase with IA, right? But it is opposing to phi P, so therefore it is of course in the direction of IA, right? Okay. Now we need to find the effective flux. If we'll add phi P plus phi AR, then I will get phi E, which is the effective flux. Okay? Effective flux. Now it is added together, phi P plus phi AR. Of course, their vector sum. So phi E is your effective flux, right? Now with respect to the effective flux, we will have a voltage induced, that is called effective EMF, right? And it is mentioned here as EE, which is the effective induced voltage. Okay? So therefore this effective induced voltage, and what is the relationship between effective induced voltage and the net induced voltage? That EA plus EAR is equal to EE, right? Okay, is it clear? So this EAR it is because of this flux, it is because of the phi AR. As we can see here, phi AR, EAR is induced lagging to the phi AR because phi AR is in this direction, phi AR. So it is lagging by 90 degree, right, to phi AR, right, EAR. So now EAR plus EA will give me effective voltage, and this effective voltage will be in fact equal to VA plus IARA plus J of IAXL. That is the effective voltage I am getting across, or the induced effective voltage, right? Okay. VA is the terminal voltage. So now I hope it is clear, this diagram, considering Phasor diagram, considering the armature reaction. Is there any doubt in this? This is for the unity power factor. Now I will ask you to draw for the lagging power factor. Please do it. Okay, now we are talking about the lagging power factor. This is your figure, right? So for lagging power factor, of course, your IA will lag the terminal voltage PA, and similarly your phi P and phi AR you can draw, right? And then effective flux phi E and effective voltage, then EAR, EA. So all the components you must draw. Okay, that will be, then it will give a clear picture. Okay. Now what we are observing here is EA plus EAR is the EE, which is the effective induced EMF, right? Okay. Similarly, we can see here for the leading power factor. Okay, this is your diagram for the leading power factor, where the current is leading the voltage VA, terminal voltage, and accordingly we can see here the phi AR and phi P, phi AR, and effective flux, then your EAR, right, and EA, right. So okay, so then your effective induced EMF is here, which is lesser than the terminal voltage for the leading power factor. So I hope everybody is clear.
Yes, sir.
Okay. Okay, now because EAR, this is one of the phasor, voltage phasor, so I can write this in terms of XM. XM is your magnetizing reactance in the armature circuit. I can write it as minus of JIAXM because it is opposing to the actual voltage induced, right? So therefore I can write it here, X is equal to XM plus XA, and Z is equal to RA plus JXS, because your, of course I can write here VA will be equal to EA minus IA RA plus JXS. So EA minus IA RA minus of IA JXS. XS is your XM plus XA. I can substitute here XM plus XA. Okay. So this XM component is your, because of the magnetizing reactance, and XA is normal leakage reactance, right? As you have also seen in case of transformer. So now this IAXM will give us the component because of the armature reaction, okay, and IAXA will give us the drop because of the leakage reactance, okay. So now if we'll talk about the voltage regulation, so voltage regulation I can write the same way whatever we have written, the no load voltage minus full load voltage by full load voltage into 100, that will give me percentage voltage regulation. So EA, of course, it is the no load voltage across the terminal. When the load is not there, we'll find the induced voltage, right? Now the diagram is more clear here. Okay, you can see here, this is your diagram for the unity power factor. Now this is for the lagging power factor. This is for the unity power factor, and this is for leading power factor. And excess is known as, sometimes it is known as synchronous reactance. Okay, and XA is your leakage reactance, and XM is your magnetizing reactance. It is similar to the transformer we have seen, right? Magnetizing reactance. Okay, so XS is your synchronous reactance. Okay, now this is a problem, very easy problem. Can you do this? So now you can see the answers. First you need to find the phase voltage, okay? Because the parameters are given in the phase quantity, right? Per phase. And IA we need to find from the kVA rating of the generator. It is 25 ampere. Then let us find for the lagging power factor. For the lagging power factor of 0.8, the phase angle will be minus 36.87. And now your induced EMF will be 120, that is the terminal voltage, plus RA plus JXS into the current. Current is 25 ampere. Current is lagging by minus 36.87. Because we are considering here VA, terminal voltage, as the phase reference phasor. Okay, so now I got EA as 233.77, 28.21 is the phase angle. Now we can find the voltage regulation. It is 94.8%. Okay. Now coming to unity power factor, theta is equal to 0, right? Similar way you can do it. We'll find the EA, generated voltage, then voltage regulation, okay? And here we are finding the voltage regulation as 55.03%, right? Then for leading power factor, in the same way if we'll proceed, we'll find EA 119.69, 71.49. Voltage regulation is minus, it is coming negative, minus 0.26. So whenever the voltage regulation is negative, means your terminal voltage is greater than the generated voltage or induced EMF, right? Okay, I hope you understood this. Okay, tomorrow we'll see this concept, not tomorrow, next class we'll see this power relation. Okay.